Okay, hi guys. So in this lecture, we'll be continuing on seeing more on alpha, beta, and gamma particles. So if we have to compare the velocity of these particles, then the velocity order is the velocity of gamma would be the highest, then beta, and then alpha particle. Okay, if we talk about the penetration power, then the penetration power would be high of again gamma particle, then beta particle, then alpha particle. If we talk about ionization power, so the order of ionization power would be alpha particle would have the high ionization power than beta, which would be having high ionization power than gamma particle. Okay, so suppose we have a radioactive element placed here, something like this. Okay, so we have a negative plate here and we have a positive plate here. So suppose this is a radioactive element and this emits all the three particles. So gamma particle would go actually undeflected like this. Alpha particle would go towards negative charge plate and beta particle would go towards positive charge plate, where this is a radioactive element. Okay, next important point is that all radioactive elements disintegrate, or rather the disintegration of all radioactive elements follow first order kinetics. So all radioactive elements disintegration follows first order kinetics. Okay, next let us see a reaction rather of a radioactive element in which a radioactive element A converts into B plus C. A is a radioactive element. Okay, so we can write that minus dN over dt would be equals to lambda times n. Okay, so where lambda is nothing but the decay constant and n is the number of nuclei of A at time t. Okay, so we can also write a would be equals to lambda n, where we can write that the rate of decay or disintegration of a radioactive element can be written as A equals to minus dN upon dt. Minus dN upon dt. So which is nothing but the rate of decay or disintegration of a radioactive element, which is also called A is nothing but activity. So activity is defined as rate of decay or disintegration of a radioactive element. Okay, Now we can also write n, which is number of nuclei of A at a time t, as W by m times Avogadro number, which is nothing, W by m is nothing but the number of moles into Avogadro number. This much amount of nuclei or number of nuclei would be present. Okay, so activity can then be written as lambda times W upon m times Na. Okay. So let us write that suppose initial activity is A naught equals to lambda times n naught. So n naught is the initial number of nuclei of A, which can also be written as A naught equals to lambda times W naught upon n, other capital M, times Avogadro number. Okay, and we also know that A is equals to lambda times n is W by m into Na. So if we take the ratio of A naught upon A, so A naught upon A would give us W naught upon W, which would also be equals to n naught upon n, which would also be equals to number of initial moles divided by number of moles at time t. Okay, so let us now discuss the unit or are the units of activity. So units of activity would be, suppose 1 Ci would be equals to 3.7 to 10 raised to power 10 dps, and dps is the disintegration per second. Okay, similarly we can write dpm as disintegration per minute. Okay, so we can write that 1 milli Ci would be equals to 3.7 into 10 raised to power 7 dps, and 1 mu Ci can be written as 3.7 into 10 raised to power 4 dps. Okay, so SI unit, this is the first unit, which is Ci. Second we have SI unit, which is becquerel. Okay, so 1 BQ is equals to 1 disintegration per second. Okay, so we can write that as 1 Ci is 3.7 to 10 to the power 10 dps and 1 dps is equals to 1 becquerel, so we can write that 1 Ci would be equals to 3.7 times 10 to the power how much dps, so it would be 3.7 to 10 to the power 10. Just substitute the value here. By the way, Ci is Curie. Okay, so Ci is the short form for the unit, which is Curie. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing specific activity. Okay, so till then, good luck and goodbye.